What should be my stage name? Dr. Mike Drop.
That could be the name of your podcast.
Dr. Mike Drop, the name of my podcast. I don't think, you all have to listen to me enough with just this class. I mean, long form podcasts, no.
I listen to your recordings.
No.
I think you have so many views. I turn them on and I go to sleep.
Like, very pleasant way of saying, you are the most boring guy ever.
No, it's just the sound quality.
Oh, okay.
Calming voice.
Okay.
Yeah. Subconscious studying. It's a real thing.
Let's get into lecture 20. How about that? All right. Let's get started. I'll say something about this lecture. This is going to be an odd statement to make, but I don't actually always teach this topic. I'm actually kind of excited about it because we have had a fairly gentle winter in terms of snow days. If there's any one topic that I cancel, it's this one. Okay. But I guess the other downside to that is I actually don't have this problem worked out with me today, so we're going to have to do this one live. So I am definitely going to need your all's help today. Because that's what, you all have your Casio FX115 ES classes or similar scientific calculator. Okay, still working on catching up on homework. The workable gauge table, I think, like we had some discussion before class. Other than that, that was probably, the homework went well, but did that part, everybody seem to kind of navigate that all right? Again, that workable gauge table was really only meant to help you place the bolts transversely, but transverse placement doesn't really affect bolt bearing capacity calculations. It's the longitudinal placement, and that didn't change. That's just, edge distances and spacings and whatnot. So, okay. All right. So today's an interesting topic, but it is leaning into a general class of problems in structural engineering that happen every now and then, and these are problems dealing with elements under combined loading. Now, I am just curious, how many of you have had reinforced concrete design? I'm just curious. We've got a couple of you in here. So did you discuss beam columns in reinforced concrete? So the idea you have a beam and then a column, but then one that's experienced both axial and bending, and you have those interaction charts that sort of look like this, like you've got that, and then the interaction chart kind of looks like that. You don't know what I'm talking about. If those of you that have had concrete design, you've seen it. If not, if you do take concrete design, you will see it at some point. But essentially, a beam column in reinforced concrete is when you have an element that is both being pushed on and bent at the same time, okay? And so the idea is that you can't really treat, you can start the problem by treating those independently, like look at the axial load versus its axial capacity, looking at the bending moment versus its flexural capacity. But at some point, you have to consider the interaction between the two, okay? And so in concrete design, those curves are called interaction diagrams, that's what they are. We're going to deal with that somewhat similarly in here. We're going to have a situation with bolts under combined loading. And so we're going to look at their shear capacity, their tensile capacity, and then the interaction between them, okay? Let's just recall our bolt shear and bolt bearing capacity. We're actually not going to do bolt bearing today. We're just going to worry about the interaction part today. So just bolt shear, and then our new limit state, bolt tension, and then the new limit state on top of that, the interaction. So bolt shear, again, pretty simple lookup, okay? Pretty straightforward. Okay, bolts under combined loading, okay? So in order to describe bolts under combined loading, I'm going to have to take a little bit of a sidebar and talk about bolts in tension, and then we'll talk about bolts in tension and in shear. So just to make sure that everybody's on the same page with what I'm talking about, let's imagine for the sake of discussion that this is a bolt, okay? So when I say a bolt in shear, I'm talking about taking the bolt and shearing it like this, okay? So like let's say my left hand going towards you, my right hand going away from you, and I'm talking about that type of effect, okay? That's shear, okay? Tension is taking the bolt and yanking on it, okay? interaction or tension and shear is what would happen if both of those were happening at the same time. Okay? You might go, well, when is that going to be the case? I got a really simple example of when it would. But let's take it one step at a time. The first thing I want to discuss is bolts experiencing tension. Okay? Now, to be clear to everybody here, we have already dealt with threaded parts and tension. We already did that when we looked at threaded rods, right? With threaded rods, we had essentially threaded parts and tension. Now we're dealing with bolts and tension, so the lookups are a little different, but the process is the same. So to give you kind of a real-world example of what I'm talking about, like if all we were looking at is bolts and tension, we'd be looking at this. This is a sort of a hanger style connection. And there are elements of this connection where you would need to check the capacity of the base metal or the plate, the WT itself. Like there's a phenomenon called prying action that might happen. We're not going to worry about that in here, but there are situations where you would need to consider the strength of the WT in this connection as well. But right now I'm just focused on the bolts. Now the tensile capacity of the bolt is just the stress times the area and then a phi value of 0.75. Just like with bolts and shear and with slip, there is a design aid for bolts and tension. It is a lot easier to deal with bolts and tension computationally than it is bolts and shear, because it doesn't matter whether threads are included or excluded from the shear plane, because there is no shear plane. You're not shearing anything. You're loading it in tension. And it also doesn't matter how many shear planes there are, because there's no shear. You're just yanking on it in tension. So really all it is here's the stress, here's the diameter, there's the answer. It's that simple. So the 7-2 design aid for tension is a lot more compact than it is for shear, because with shear there's a lot more variables. Is it single shears, double shears, threads included, threads excluded? So if you look, the table 7-1 is longer than 7-2 because there's more going on. Does that make sense? So if we have a connection, if we wanted to check bolt shear capacity, take the shear load per bolt, compare it to the shear capacity of a single bolt. Same thing with tension. If we have a bolt group experiencing tension, take the tensile load per bolt, divide that by, or compare that against the tensile capacity per bolt. And again, you could divide and do a performance ratio or something like that, but again, just check each one at a time. But again, that doesn't quite answer the question about interaction. What about interaction? So a classic example of when bolt groups would experience shear and tension is this, okay? So here I have sort of a column and I have a bracing style connection, and I'm yanking on that connection like this. So notice how I've got this 3-4 slope ratio here, right? So maybe a little bit of trig going on. So with this situation, I've got, this PU, I can separate that into a tensile load and a shear load using a little bit of trig, right? Okay? So when we have problems like this, we have to consider the capacity of the bolt group in shear, the capacity of the bolt group in tension, and then what happens with the interaction between the two. Okay? And that term interaction, I'm going to talk about that here in a little bit. But I will say that interaction is something that happens in a number of different situations in structural engineering. From a code check standpoint, typically the way interaction works, like if you have a beam column, for example, in steel design, for beam columns in steel, you typically compute the axial capacity, you compute the flexural capacity, and then you throw it into an interaction equation. So the idea is that if you know how to compute each one, then the capacity in interaction is really not that challenging. It's sort of a plug and chug. It's the capacity of each of them that's probably a little bit more computationally demanding. Now, analysis, that's another story, but we'll get to that later. Okay, everybody with me so far? Now, here's the idea behind interaction. So I've got some funky, graphs here and curves here and stuff like that. I don't want to get too far down the rabbit hole on this, but I want to explain what's going on here very broadly, very simply, okay? So here's the idea, okay? Let's say that I'm taking a bolt and I'm applying tension to it. Okay? When will the bolt fail? Well, the bolt will fail when the load reaches 100% of its tensile capacity, right? That's a really basic idea, right? So if I'm taking this bolt and yanking on it, it'll fail when it hits the tensile load, okay? But the question is, what happens if I'm taking the bolt and I'm yanking on it and shearing it at the same time, okay? The idea is that, well, if I'm looking at tension, I can't really count on 100% of the tensile capacity in that stage or in that scenario, because the bolt is also having to work to resist that shear load, right? So if you have a bunch of shear on the bolt already there, and then you ask, well, what is its tensile capacity? Its tensile capacity may be reduced. Maybe its tensile capacity is only 60% of its original capacity because of all the shear that's on. Does that make sense? The idea is that the presence of the shear on the bolt is reducing its tensile capacity. Does that make sense? Like, you can't do both at the same time with 100% efficiency. The presence of shear is going to reduce its effectiveness in resisting tension. Make sense? Okay, that's really what's going on here in this picture. Now, what we've got here in this picture is, on the x-axis we have how much shear we're putting on the bolts, and then on the y-axis we have how much tension we're putting on the bolts. Now, what this is basically saying is that if you have zero shear on the bolts, like absolutely no shear whatsoever, what is its tensile capacity? Well, it's just however much it can hold up in tension. On the flip side, what if you have absolutely no tension on the bolt? What is its shear capacity? Well, it's this right there, whatever we look up in table 7.1, okay? But what's happening in between, so like right here, it's saying if you have a bunch of shear on the bolt, your tensile capacity is going to be reduced. Now, the lab tests show that if you actually take a bunch of bolts in the lab and do this, that the data fits more this like elliptical style relationship, okay? So if you actually do this in the lab or do a bunch of modeling, this is the expression that fits the data very well in the lab. But ellipses are hard. Engineers don't like dealing with hard equations if they can avoid it. So what the spec does is the spec says, let's not do that. Let's just do a straight line fit. So basically what the spec is saying is that any time that your load, that your shear load is less than 30% of the tensile load, or vice versa, we can ignore the effects of interaction. So let me give you some numbers. Do you think that this reduction effect, this interaction effect, is really going to matter all that much if I have a bolt group that's got 100 kips in tension and 2 kips in shear? It's not going to matter, right? And what the spec is saying is that it's not really going to matter until that ratio gets above 30%. So if you have 100 kips in tension and like 80 kips in shear, well, that's a different story. That's a lot of shear compared to that tensile load. So whenever these ratios get above 30%, either here or over here, we have a straight line fit where one capacity is reduced based on the presence of the other load. Does that make sense? Everybody okay with that? Now, the way that we compute that is through the following expression, okay? So the following expression is that, so what we do is, instead of calculating like FNT times AB, we calculate this FNT prime. So it's a modified tensile capacity. And it's a modified tensile capacity based on the presence of shear, okay? Now, what is the expression for it? It's this right here. And if you look at this right here, this equation, this stuff up top, is really just y equals mx plus b, okay? Because if you look at this, what do we have? We have, this is our y-intercept, this is our line. So this is the slope, and this is x. So mx plus b. See, the slope is negative, okay? And if you look at that, if we go back a slide, this is the line that we're looking at. This is a line with a negative slope. what is the intercept of that line? The intercept is about right here. And what would that intercept be? Maybe, I don't know, 1.3 times the stress. And that's exactly what we got. 1.3 times the stress, that's our y-intercept, negative slope, and then this is our stress on the x-axis. So basically, based on how much shear stress we're putting on the connection, we reduce this a little bit. Okay. Now, if you actually read the spec, what the spec is saying is this, but remember, whenever we have a less than or equal sign, it's basically just saying the minimum of these two. Does that make sense? Okay, everybody with me on that? All right. Okay, now, here's what we're doing. Okay, I want to make sure that we're crystal clear on this. Okay, so whenever you're performing an interaction check, what we're doing is we're computing a reduced tensile capacity. So when you compute an interaction capacity, you compare it against the tensile load. So basically what the spec is saying is interaction is to compute a reduced tensile capacity. It is very possible that the spec could have been written to compute a reduced shear capacity. The effect would be the same. Really, when they wrote the spec, they just sort of like flipped the coin. Okay? So the point is, you don't compare it against the inclined load, you compare it against the tensile component. And that part might be a little fuzzy right now, but that's okay, because we got an example we're going to do here real quick where this is going to make a lot more sense. Okay? So I have here a series, or I have here a connection expression. Let me pull that up here in the notes. Okay? And like I said, I'm going to need your help on this one because I actually don't have any notes on this. We're doing this live. Okay? So I have here an inclined load. So this bolt group is going to experience shear and tension. Okay? And we're going to analyze this connection to see whether or not it's got enough capacity to resist these applied loads. So I have a dead load of 15 kips and a live load of 45 kips. I've got group 120X bolts, and we have a 3/4 inch diameter bolt in this bolt group. Okay? So what we're going to do first off is deal with these loads. Okay? Now, the first thing I'll point out before we move on, how many bolts are present in this bolt group? 4. Okay? Because what's going on is something like that. And so there's a bolt here, but then there's also like a bolt there and a bolt there, like on the other flange back here. Does that make sense? So, okay. I hope that was clear. Okay. All right. So I'm going to erase this because I kind of need this space over here. Okay. So first thing I'm going to do is factored load. Okay. So the first thing I'm going to do, so this first part is really just dealing with the loads and the stresses and the analysis side of things. Okay. So first off, let's deal with the factored load. Okay, so what do we got? 1.2 dead plus 1.6 live. 85.5 kips. Do I have a second on that? I'm not hearing anybody. 1.2 dead plus 1.6 live. Okay. Is it 90 kips? Okay, everybody good on 90? Okay, all right. Now, okay, so what we've got going on here is we have a column that's experiencing an angled load of 90 kips, okay? And it's an angled load at a 3 to 4 slope ratio. So 4 on the horizontal, 3 on the vertical. So what's the hypotenuse? 5. There we go. 3, 4, 5 triangle. Okay. So the first thing I want to do is I want to see if I can determine VU and TU. Okay. So to be clear, what I'm talking about is this component and this component. Now, let's just be clear. This horizontal component, is that tension or is that shear? Tension. I'm yanking on the bolts. Yes, this is tension. So we'll call this TU and we'll call this VU for shear. Okay? So I propose that both of these are going to be PU times some fraction. What are those fractions? Okay, what is the fraction here for VU? 3 over 5. And the one down here? 4 over 5. Okay, so the idea is that if this was a right triangle, the original load is the hypotenuse. Okay, and the components, the shear and the tension, are the legs of that triangle. So which leg is bigger? Well, the bigger leg is whichever one has the bigger number. So the denominator here is always going to be the hypotenuse. Okay? So what do we got for this? 54 and 72. Okay, that was definitely seconded. I only heard one person say 54. We're good on that? Yeah. Okay, all right. Okay, everybody with me so far? Okay, now I'm going to compute a couple of other things off to the side just to make sure that we've got all of our analysis done. Okay? The first thing I'm going to do is I'm going to compute VU per bolt and TU per bolt. Okay? So, in other words, the connection has 54 kips in shear. How much on each bolt? And how do I get that? I just divide by the number of bolts. And so, what do we get here? Second? Okay. And then, here, let me drag that down. I must say, I get spoiled to that because you can't do that on a whiteboard. Ah. Okay, I can do better than that. 72. And 72 divided by 4, what, 36, 18? Yeah. Okay. So far, so good? Okay. All right. Now, the last thing that I am going to compute is this term required shear stress, FRV. And FRV is really just a fancy way of saying what is the shear stress on the bolt group. Okay? Now there are two ways to compute it and you will get the same answer. Okay? But before we get to that, we need to compute the area of the bolt. Okay? Now what is the area of the bolt? How do we compute that? Well, okay, okay. You are right. We can look it up. And what is the area of a bolt? 0.442, which is from table 7-1. Okay? But if you don't recognize that, you can always just say pi over 4 dB squared, which is pi over 4 times 3/4 squared, which is again 0.442. Okay? Sound good? Or maybe what we should do is say inches squared per bolt. Because, I mean, that's like actually what's going on. That's the square inches per bolt. Sound good? Okay. All right. So, how do we compute FRV? Well, I propose that there are two ways of doing it. The first way is to take the shear per bolt and divide it by the area of a bolt. The other way of doing it is to take the shear load and the total shear and divide it by the total area. Either one's going to give you the same answer, right? Because VU per bolt is equal to VU over NB, and that's what this is right here. So it's going to give you the same answer. I'm going to use the first one because I'm lazy. So this is 18 kips per bolt divided by 0.442 inches squared per bolt. Oh, you're right, you're right. Thank you. You are right. .05 on the mistake counter. 30.5 what? 30.54. Do I have a second? Yeah. What are the units?
Kips per square inch.
Exactly. This is KSI. Okay. All right. So far, so good? Okay. Now, some of you might ask, well, do you need a required tensile stress? No, you do not, okay? Because we are going to use this term to compute a modified tensile capacity. We could theoretically compute a modified tensile stress to compute an interacting shear capacity, but that's not the way the spec's written. So no, we do not need that. Okay. Now, in order to handle this, what we're going to do is we're going to check three limits. Now, some of you are going to think, well, the first two don't really make or aren't really necessary because of interaction. But I think it's good practice to go ahead and just do them all. Because if you're failing one of the individual checks, you're not going to pass interaction, right? You're just not going to, okay? So you might as well just check them all, okay? Make sense? So just bear with me, okay? So let's look at each of our limit states. Okay. Remind me, what was the group? Threads included or excluded?
Excluded.
Are we in single or double? Single shear. So, based on this, what is my VRN?
2.5.
Do I have a second on that?
Second.
Okay, and that comes from table 7.1. Okay. What do I compare this to? Can I compare it to something just right now?
Shear tension. Yeah, shear tension per bolt.
No, hold on. Not the shear and tension. So this is a bolt shear capacity.
Just the shear.
But which one? Per bolt, right? So that was one of the benefits of doing this. See, before what we would do is take this, multiply it by the number of bolts, and then compare it against the total shear. But we went ahead and computed this. So why don't we just say, okay, we have a shear capacity per bolt. We have a shear load per bolt. and that is 13.5 kips per bolt. Can I make any conclusions about this limit state right now? So far, so good. We satisfy this limit state. Done. We have now satisfied this limit state, okay? Because before we would have to multiply by the number of bolts, but in this problem, we did it the other way around. We divided here, so we don't have to worry about that. So now we're going to get some experience in Table 7.2. We haven't looked at Table 7.2 before, so let's look at Table 7.2. It's right next to it. So bolt tensile capacity. What information do we need about the bolt in order to compute bolt tensile capacity? Do we care whether or not the bolt's in single shear? Not for tension, right? Do we care about whether the threads are included or excluded? Not for tension. Only thing we care about is two things. What group it's in, and what's the bolt diameter? And what is phi RN? 29. And likewise, we compare that against what? The tension per bolt. And what was the tension per bolt? 18. So, what's the deal? We're good. All right. And I do think it's worthwhile to go ahead and do this check in the real world, because if you don't meet these two limit states, you are not going to meet interaction. Like, you're just not going to. So you might as well do these first. And they're really easy to do. And plus, you need these values anyways in order to do the interaction check. So you might as well just do it. Okay. All right. Okay, so for bolt interaction, okay, let's go back to here. It doesn't like me when I do that. Okay, so here's the expression that we're using. Okay, so this is going to be the expression that we use to compute FNT prime, because that's going to be the first goal that we have to do. So we need an FRV, but we already got that, right? That was 30.54 KSI. We need a phi value. What is phi? It is 0.75, right? But we need an FNT and an FNB. Does anybody remember where to get those? Anybody remember where to get those? Let's go back to this. We haven't looked at this in a while. Here, I'll pull it up here. We got time. So here's our specification. You all have this in the back of the manual. It's 16.1 dash, I think like 140 something. Sorry, 137. Oh. Whoops. Okay, here we go. So this is 16.1-137. We have group 120 bolts with the threads excluded, right? We looked at this a long time ago, because remember we said we're going to look at this to compute shear capacity of a bolt, and then we're not going to look at it. Well, we're not going to look at it to compute shear capacity, but for interaction, we do kind of need these values, because our interaction capacity is based on the raw capacity of each one. So we have our nominal tensile stress of 90 KSI and our nominal shear stress of what? Which one? 60. 68 because the threads are excluded. So we got 90 and 68. So what I'll say and let's not forget that we computed this is 30.54 KSI. Okay? With me so far? Okay. So, what I'm going to do is I'm going to compute a new FNT, an FNT prime. So an FNT, it's going to be reduced from this, probably going to be reduced from this based on the presence of shear. Okay? And we'll talk about whether or not we could predict if interaction was a problem here in a little bit. Okay, so minimum of. All right. Did I get that right? Make sure. Let's see. FNT, FT, FV. Yep, got that right. Okay. So here's our expression that we're going to do. All right. And let's see. Let's start checking this out. All right. So 1.3. Oh, I can do better than that. I'll use brackets. We don't need curly braces. $90 KSI to what? 63.12. Okay. So what this is saying is that if there were no shear present at all, this is the tensile capacity right here. But because we got all this shear stress on here, this is our actual tensile capacity based on the interaction between the two. So the fact that the bolts are having to hold up all that shear reduces their ability to hold up all that tension. That's what this is saying. Okay, does that make sense? So now what we're going to do is we're going to compute a new phi RN. Maybe we'll call it a phi RN prime if we want. So that's phi FNT prime AB. So what do we get for phi RN? Or phi RN prime, I guess we should say. 20.9 kips per bolt. We'll just say 20.9. Do I have a second on that? All right. Now, so that we are clear, what do I compare this to? So what is this? This is a reduced tensile capacity. That's what we're doing. Sorry, what? Not, well, not the stress, but you're right, not the tensile stress. This is the shear, or sorry, this is the tensile capacity per bolt. Compare it to the tensile load per bolt. Does that make sense? And what is the tensile load per bolt? 18. So what does that mean? We're good. So what is the answer? Sorry, what is the answer to the problem? The connection is adequate. Okay? Everybody with me? Now let's make a few observations, okay? Let's think in terms of performance ratios. I mean, what would the performance ratio on this be? I'm just curious. We'll put a performance ratio out here. 86%. So when I say performance ratio, I mean the efficiency, just that divided by that, right? Now, that performance ratio is a heck of a lot better than the performance ratios for these two, right? You see what I mean? So here's my point. If we didn't have to worry about interaction, would it be fair to say that it almost looks like this connection's over-designed? Yeah, it's pretty over-designed, right? Because without interaction, all we're comparing is tensile capacity to tensile load, and this is certainly fine, right? Okay? So I think the point I want to make is what that's doing to the efficiency of the connection as a whole. The other thing from a connection design efficiency standpoint, I mean, is there any way we could make this connection more efficient? I mean, it's got 4 bolts in it. Could we do 2 bolts? No, it wouldn't work, right? And 6 bolts wouldn't make any sense. And I would also argue an odd number of bolts wouldn't make sense because then it wouldn't be symmetric, right? Which would create imbalances in how the load's being resisted. All right. The only other thing I want to mention is there any way that you could look at these 2 numbers right here and tell me whether or not interaction would be a worthwhile check?
Within 30% of each other?
They're within 30% of each other, right? If this was 72 and this was 6, wouldn't matter, right? What is 30% of 72? What is that? 7.2. It's like 21.6. So as long as this number is bigger than 21.6, that means you need to do interaction. That's what that's saying. So what I'm getting at is we could have looked at the very beginning of the problem and we could have said, yeah, we're going to have to do an interaction check. You know, it's going to be necessary. With me so far? Any questions? All right, well, the only thing I have left for you is a final homework on bolts. And with this one, the only difference is trig. Like, so instead of a 3 to 4, I gave you an angle. So you got to break out those lovely little sines and cosines. So I'd argue it's actually kind of easier than having to figure out whether it's a 5 on the denominator or which the 3 and the 4, because you can just do some sines and cosines on this one. So I'd argue it's easier. So sound good? I'm going to pull the code up again and give you an extra 5 minutes on this lovely Friday. You all have a wonderful weekend.